Okay. So, I think the last definition we were looking at was Wilhelm's classes. Okay, that. And we continue with the next definition. This will be about functions. Okay, so that is next. So guys, what is a function? You know what the relation is. Okay, so a relation is actually a subset of a Cartesian product. Okay, so suppose. Okay, so this is going to be definition. So let me just introduce it to you. Okay. Okay, so suppose that suppose that f is a relation on the Cartesian product a by b. Okay, so which means that it's a subset. Okay, let me just give that here to you. Okay, so f is a subset of the Cartesian product, and you know what a Cartesian product is, you know what a subset is. Okay, I hope you don't forget these things. All right, then. So here in that case, if for all x from the set A, there is exactly one y from the set B that satisfies the following relation, namely that y is of f of x. So that means that here in this case, x relates to y. Okay, so if only one y relates to x, exactly one y in that case, then the relation, so the relation f is called function, and that is actually the notation we use. Okay. So I mean, this is actually the definition here, and for that we just write like this. Okay. So here in that case, x related to y if and only if y is equal to so-called f of x. So this means that here, for instance, that case. Okay. So y is called the image. Okay. So here in that case, x is called the argument of the function. And y and f of x are called images, okay, of x under f. Okay. Now this is something that you might see, okay, but probably no one actually told you that relation is a function here as well. Okay, so in that case we have a relation where for each element that we use here from this set A, there is just one and only one element from the set B. Okay, so that's the difference. Okay, so I actually can see it. So there is just only one image, let's say. Okay, and this is what the function is about. Okay, now you can say that this is the argument, or you can say that the pre-image. I mean, I'll give you an example for this, so then you've probably seen this. I mean, this is relatively easy. Suppose that we have the second real number twice, so we define actual relation of the Cartesian product of A r by r, which is r squared, right? And suppose that the function is given like, for instance, this is x squared, so this is the parabola. So then what we actually, of course, you already know that if you put in 2 into the function, then you get 4. So this means that the image, okay, so the image of 2 is 4. Okay, so this is the example that I gave you here. I hope you understand that. Okay, so 2 is the argument, the image is 4. All right, and what you can say is that what's going to be the pre-image? I mean, this is actually how you call the pre-image. So let me just give that to you. So this is the notation for the pre-image. Okay, so what's the pre-image? Actually, a 4. So the question is, what do you have to put into the function to get number 4? I mean, this is relatively easy. I hope you understand this. Right, so 2 and negative 2. Okay? So the set consisting of 2 and negative 2 is considered to be the pre-image of 4. Okay? So this set here, 2 and negative 2, is the pre-image of 4. You understand? Pre-image. Okay? And this is just a new expression. Okay? In Deutsch, as in German, say Urbild. Okay? Pre-image. All right? Good. Okay, so I mean, you're all familiar with this, but I would like to actually to give you the relation between relations and functions. So that's just how it works. Okay. So for a function is actually a relation where just there is only just one image, one and only one image for each element to which the image is related to. Okay. So this is what it is. Now, next definition, I'm going to talk about so-called injective, surjective, and bijective functions. So this is going to be next. Okay. So a function is called, so let's start with that. So injective. Okay, this is nothing to do with injections from a medical perspective. Okay, so the function is called injective if, let's say, two different arguments always have two different images. Okay, so if two different arguments always, okay, let me just give that, I'll write it down here so you see better. Arguments, hopefully, always have two different images. Okay? So if the arguments are different, then actually the images must be also different. See? Okay? So in that case, I mean, from the formal perspective, you can write it like this. So let's say f of x1 is equal to f of x2, then this implies that x1 is equal to x2. Okay, so if you go back to propositional calculus, you see that this condition is necessary for that one. Okay, so if that is not satisfied, so if the arguments are unequal, then what? Then the images of the corresponding arguments are also unequal. You understand? Okay, so they are not equal either in that sense. Okay, so this is necessary for this to hold. Remember? Okay, so that was what we did last Friday. Okay, so two different images always have to have, two different arguments always have to have two different images. So in that case, the function is called injective. Later, I'm going to give you an example of that. So the function is called surjective. Okay, so f here in that case. Okay. So f here is called, and it's just if. Okay, so in that case, let me just, because I forgot the notation. If for, let's say, if there is always at least one pre-image, okay, in the set of all images. So let me just give you that notation here for the function that goes from A to B. This is the notation that we have. There is always a non-empty pre-image for any element from B. Okay? So the image of any element from B is not empty. Okay? So that means that there is at least one pre-image element. Okay? So this is the executive definition. So for all elements from B, there is at least one element from A, which is supposed to be the element of the pre-image as well. Okay? And the function is called bijective. Okay? If it is both, right? So it is both, that's easy, surjective and injective. maybe I just should add the formal definition for surjectivity here. Okay, so this is what I do here. Okay, and we can just give you, maybe you should have a little bit more space. So let me just write it down again. It was not long, okay, so don't worry, but I need more space. So the function is called bijective. Okay, if it is injective and surjective. So it has to be both. Okay? And the formal definition of surjectivity is as follows. So that means that for all elements from the set B, there is at least one element from A where the function satisfies that y is equal to f of x. Okay? So that is. So there is always at least one element. That's the definition. Okay? Now let me give you an example, so you see the problem with that. Okay? So let's consider the parabola again, and we will find that the parabola, if it's defined, so this is going to be the example. Here for the parabola, okay, so suppose that we define the parabola from R to R, okay? And I will show you that actually the function here, given by the equation f of x equals x squared, is neither injective nor surjective. Okay, so here in this case, the function will not be surjective, and the function will be not injective. Okay, so first off, let me just examine the injectivity of the function. Now, why is that? Why is the function not injective? I mean, what does injectivity means? It means that two different arguments always have to have two different images. So for instance, suppose that we have f of 2 equals 4, and f of negative 2 equals also 4, right? You see this? So in that case, that means that the condition that two different images always have two different arguments, sorry, always have two different images is actually not satisfied here. So let's say if the images are equal, right? If the images are equal, then this does not imply that actually that the arguments are equal. You understand? Okay, so here in this example, because f of 2 equals 4, so the image of 2 is 4, and the image of negative 2 is also 4. So in that case, we have that if the images are equal, that this doesn't imply that the arguments are equal. Namely that two different arguments do not always have two different images. You understand? Okay, so hence the function, okay, hence the function f of x equals x squared is not injective. Okay. All right, and you can, of course, you can show this in general case, but as soon as I find an example that two different arguments do not have two different images, then actually I've shown that the function is not injective. Okay, so you can use, of course, the more general approach, which is given by the example, but you can see this here. All right, okay, and the function is not surjective either. Okay, so you can see this here. So what about the surjectivity of the function? Okay, so every element has to have at least one pre-image, okay, which is not empty. So for instance, if let's say, I'm giving you just the function again, so what would be, for instance, the pre-image of negative 1, okay? Let me just add this here. So pre-image of negative 1. Okay. So what would be actually the corresponding argument where we would have actually that the image of the argument would be equal to negative 1. So in instance, what is the pre-image of negative 1 here in this case? What do you think? What is the pre-image of negative 1? Is there actually an argument that has an image of negative 1, guys? No, right? So there are none. So the pre-image of negative 1 is actually empty. Or you can say that negative 1 does not have a pre-image, okay? formal sense. But that is actually the formal notation because the preimage is actually supposed to be a set, okay? All right, so hence in that case, the preimage of -1 is actually empty. So in that case, it means that the function is not surjective because there is at least one element from this set here, okay? So the set was here, the second one, all right? So there is at least one element from, okay, where the preimage is actually empty, okay? Okay, so there is at least one element from this set R for which the preimage is empty. Okay, of course under the function. So in that case, that means that this implies that the function is not surjective. All right. Okay. You understand this? Yeah.
If you define this function from the real numbers as a mapping from the real numbers
Yes.
to positive real
Yes.
numbers, in this case it would be surjective.
Exactly. Okay. So in that case, let me just give you another example, and this is what I would like you to add here. Okay. I'm going to start a new page. All right. So just going to get in because I have to start a new page. Okay. But is this clear, guys? Okay. So there is no element here for -1 as a preimage. Okay. Good. Now let's continue. All right. So I'm going to save this, and I'm just going to pick up the example that you were mentioning. So this is going to be the example that we define here. So suppose we find a function from R to the set of positive real numbers, okay? Positive real numbers including 0, okay? I hope you are familiar with this, okay? So these are positive real numbers including 0. Okay, I hope you're familiar with this notation. Okay, and suppose that we have actually the parabola, which means that f of x equals x squared, right? You actually know how the function looks like, all right? But actually the set of all images is denoted by r plus 0, so that means that we have just the non-negative real numbers. Now in this case, what about if we have just the non-negative real numbers? Okay, so just let me examine the surjectivity in general case. Okay. So what is the surjectivity of the function? So suppose that we have, let's say, y equals x squared, where actually x is from the set R, okay, and y is from the set R plus 0, okay? So that's the actual value start. Then this is equivalent to, in that case, so if x is from the set R and y is from the set R plus, now this is going to be equivalent to that x equals what? X equals, here in this case, I mean, how would you solve that for x? Suppose that x squared is equal to something, for instance, x squared is equal to whatever, 25 or something. Then what? Then x is equal to 5 or -5 in a general case, right? Okay, you understand? But in this case, if, let's say, y is from the set R plus, then this is just going to be, y is ejected from the set R plus, so then actually this is only equal to, okay, let me just write it down here. So this is only equal to the square root of y, you understand? Okay? And this is equivalent here in that case, because actually, as you can see this here, if you would take, let's say, the negative, okay, so the negative of the square root of y is not from the set R plus 0, Okay. All right. So suppose actually that here in this case, okay, if let's say y is greater than 0. Okay. So for 0 it is, but for if y is positive, then it's not the case. Okay. So here in that case, the two expressions are equivalent. Okay. All right. So that means that this implies here that for all y from the set r plus 0, there is, okay, an x from the set of real numbers, okay, that satisfies here in this condition, and you can see this here, that y is equal to x squared. Okay. So there is, let's say, always a pre-image. Okay. Okay. You understand this? Okay. No, sorry, guys, I'm sorry, I have to cut it off because I think I made a mistake here. Okay, so basically, you can see that y is always positive. Okay, so here in this, I mean, this is not a mistake, but just a little formal. So, I mean, what is it that these two things are equal if actually y is non-negative? Okay, so that was actually correct. Okay, so that means that there is always at least one pre-image. Okay, because if y was actually negative, then the square root of y would not be defined. Okay, so that's why there is always just actually at least one pre-image. So here in that case, the function is surjective. All right. Okay, so this implies that f is surjective. Okay, guys, so here in this case, f is surjective, and if, let's say, I'll just give you another example. Okay, so for instance, let's say that the function goes from the set of real numbers, from positive real numbers, to the set of positive real numbers, and f of x is equal to x squared, then you can see that the function f of x equals x squared is both injective and surjective as well. Okay. So injectivity and surjectivity does not depend only on the function, but also on the sets on which the function is defined. Okay. So here in that case, as you can see, that is also important, guys. Okay. So the parabola can be made to a bijective function if, let's say, actually the sets are according to the function to which it's actually defined. So you can see that here if you have r plus, which is a set of all positive real numbers, and here, as it's from the beginning, and here you have the set of all images, we also r plus as well. Okay, so actually it also depends on the set on which the function is defined. So here, hence, it is bijective as well. Okay, so hence, f is bijective. Okay. So again, what does surjectivity mean? It means that two different arguments always have two different images. That's the first thing. And second, surjectivity means that there is at least one pre-image. Okay, so there is at least one pre-image for all elements from the set of all images. Okay, there is at least one pre-image. Okay, so this is what it is. Now, why is that so important, guys? It's important because a function is invertible if and only if it is bijective. Okay, so this is actually, I can give you this as a mark. Okay, a function is invertible so the function will be of the form f goes from a to b. Okay, is invertible if and only if it is bijective. Okay. So the function has to be bijective to be invertible. Now what is actually the inverse? Okay. Let's say, I mean, you know this, right? So what the inverse function is, but I have to define this as well. Okay, so let me just give you the definition. Okay. Okay, so what is an invertible function? A function, let's call it f, okay, goes from a to b, is called invertible, okay, if and only if okay, there is a function, let's call it g, okay, and the function g shall go from b to a, okay, so this is a mapping from b to a that satisfies satisfying, okay, the following. So here in that case, so f of x equals y if and only if g of y equals x, okay. So for that to be, actually to be possible, the function has to be bijective. So it has to be both injective and surjective, okay. So then we also write, so then the notation is so we call the inverse, let's say, g of y can be written as f to the power of -1. Okay, so this is the notation for the inverse, and you have probably seen this, but this is the exact definition of it. Okay. So, and of course, I told you that the function is a function is invertible if and only if it's bijective. Now let's go through that because that is important here. Okay. So why, first off, why the function has to be injective for that? Why is this the case? I mean, why is that necessary also? Okay, it is necessary because if two different images, two different arguments, so you do not have two different images, then this means that, for instance, what would be the, actually, of course, let's say you turn around so the image becomes the argument, okay? So if that would not be equal, then actually the argument here would lead to two different pre-image here in that case, okay? And this is not a function because if we assign, let's say, certain elements to y according to that function, then there has to be actually just one element only to which we assign this element here. So if, let's say, the element, the pre-image consists of multiple elements, okay, then this is no longer can be a function. Okay, so this is just a relation, okay, because there are actually more than one images of that. Okay, so that's the reason why the function has to be surjective, injective. I'm sorry, I'm very tired today. This is just because I co-faint completely, and as you notice, I'm not in the same mood as I'm supposed to be. Maybe you recognize that, so I apologize for that. Okay, but I had to cut it because it was too extreme. Just I admit. Okay, so please, I apologize for that. I think it's gonna still take 1 week or so, whatever. Okay, but I had to do it without any substitute or stuff like that. Okay. Okay, guys. So again, why is this the case that the function has to be injective? It has to be injective because here we would have two different images for one single argument. Okay. If this function for two different arguments does not lead to two different images, then a single image here would have actually two different arguments, and in that case, function g would no longer be a function anymore. Okay, so that's the reason why it has to be injective. And why is it the case that it has to be surjective as well? Because if there is no pre-image, then we cannot turn around the sets here. Okay, so if the function goes from a to b, then this function has to go from b to a. So in that case, not all elements here from b have actually an image according to that function. So in this case, the function f has to be surjective as well. Okay, so that's the case why it has to be invertible. Now, I'm not going to prove this formally, but it actually is supposed to be actually clear by now. All right. Now, yes. Yes.
Is injectivity of the original function basically the same as surjectivity of the inverted function?
It relates to that, but the problem is, I mean, this is not the case. I mean, let's just give me an example for that. Okay, so for instance, let's say the f of x, I mean, f goes from the set of real numbers to the set of real numbers, and let's take actually a parabola again. Okay, so as we see that the function is not injective because two different arguments, okay, here in this case, can have equal images, right? Now if we just, let's say, calculate the pre-image of, let's say, of the number 4, the pre-image of the number 4 would be actually, I mean, if that's the inverse of the function, let's say, then this would be actually the function g. Okay, so what would be actually g of 4 here in that case? And we would get that this is equal to 2 and negative 2 at the same time. Okay? Alright? So in that case, the function g would have actually two different images for the same argument. Now this is something that cannot be the case because g in that case would no longer be a function. Okay, so g is no longer a function.
So f is not invertible.
Yes, in that case. But so that doesn't mean that the function g here in this case is surjective because there is no such thing as a function g, right?
But if we assume
if we assume that
f is invertible, then surjectivity or vice versa of the original function is the same as.
Of course, in that case, both functions will be injective. Both functions will be bijective. Sorry. So in both cases, both functions will be injective, but the injectivity of the original function, okay, does not directly imply the surjectivity of the inverse of the function. Okay. Here in that case, it does because they're actually. I mean, if f is bijective, then and it's invertible, and then it's invertible. So in that case, the function. The inverse of the function must be also bijective because the inverse will be also invertible in that sense. Okay, so but this does not directly imply. So if the original function is injective, it doesn't imply that the inverse function is surjective automatically. Okay, so this is not the same property as you see.
But what I meant was just it's basically the same idea, just because we flip the spaces.
Yes.
And yeah. So
but if you change it, if let's say just for the argumentation's sake, just because if we swap the two sets, right? It does not mean, all right. So if let's say if the original function was injective, it does not necessarily mean that the two different arguments of the inverse function also have two different images. Okay. So that's the thing. Okay. All right. So let's say if a certain relation has two different outcomes for the same input, then this relation is no longer a function, okay? Because there are two different images for the same argument here in that case. Okay? So g would not be a function here in that case. Good. Now let's continue, guys. Why? Because that's a very important concept, and I would like you to continue here. Okay. All right, so, I mean, why is the concept of bijectivity so important? Okay, so let's say, you can say that the sets, the sets, so the sets A and B are said to be of equal size, okay, or you can say, or said to have the same cardinality, okay, so the sizes of the two sets are equal, okay, equal size, or said to have equal cardinalities. Okay, so cardinality is what you're actually talking about. If there is exists a bijective function from A to B. Okay. Let me demonstrate that. Okay, so why it is. Okay, so suppose you have, let's say, two sets. All right. So let's say here, for instance, you have set A, and in set A there are actually, you know, there are what? There are the numbers 1, 2, and 3. Okay, and in set B there are, okay, so this is set B here. There are, let's say, 3 different letters. Let's say A, B, and C. Okay. And if we define, for instance, a function, okay, a function, let's say f from A to B as follows, okay, and then you can see, for instance, let's say that the image of the number 1 shall be, let's say, B or something, okay. I put this in quotation marks, guys. Okay, so then the image of, let's say, 2 shall be equal to, let's say, A, okay, and the image of 3 shall be equal to C. All right, so in that case, you can clearly see that the function f is bijective. Okay. Okay. Is this clear why this is the case? Guys, I mean, why is a function bijective? It is bijective because, first off, it is injective, so that means that 2 different arguments always have 2 different images. I mean, that's the case. Okay, so nowhere actually here in this case they are equal. And the second, because for all elements here from the set B, A, B, C, okay, I actually should not supposed to use capital letters here because it makes it up. I'm sorry about it. Okay, as I said, I'm kind of stupid today. I hope you apologize for that. So I'm using small letters here. Okay, because capital A and capital B were defined for the sets on which the function is created. So I apologize for that, guys. Okay, you see? So basically, what you have is that the function is injective. And since there is actually a function which is injective from A to B, then we can say that the 2 sets are actually of equal size. Okay? So the size of the 2 sets are equal. We can say the cardinality of the 2 sets is equal. Okay, so you can bijective. And then you can say that for the cardinality, right, so actually something like the absolute value, so the number of elements that are in the set A are equal of the set B. Now this is obvious, guys, because here in this case we have 3 elements from in this set and 3 elements on the original set. But we would like to extend that definition to, let's say, to sets that have infinitely many elements, because just because there are sets that have infinitely many elements, there are sets that even have more than infinitely many elements. Okay, so see what I'm saying? So this is what I would like you to actually to realize here. Okay. All right. So basically, we have that the number is actually the number of elements each set has is actually 3, and this is the cardinality of the sets. Okay. And here in this case, so the number 3 is called the cardinal number. Okay. So these are cardinal numbers. Okay. So basically what we have here is that we assign a so-called cardinal numbers. So cardinal numbers refer to the number of elements in the set has. Okay? Okay? Now guys, this is not, of course, this is obvious, okay? But we would like to actually express, for instance, what is the cardinality of the set of natural numbers. Okay? This is what we're going to talk about next. Okay? So the set of natural numbers, and let me just continue with the next example. So what would be here in this case? So the set of natural numbers. Okay, and let me just give you an example. The set of natural numbers. Okay. and I include 0 into that set, so include 0 is, of course, the notation for that is, as you can see this here, so this is 0, 1, 2, 3, 4, etc., etc. Okay? Now, basically, the question here would be, what is, for instance, the cardinality of the set of natural numbers? Or is, for instance, the cardinality of the set of, let's say, a set of rational numbers, because the set of rational numbers, as you know, consists of all fractions, is that, for instance, greater than that of the natural numbers? Now, what we do is we assign, okay, so we assign the cardinality of the set of natural numbers to be a certain number from the Hebrew alphabet. I'm not sure if you speak Hebrew or not. Okay, maybe one or two people speak Hebrew. I mean, I don't, but some of my friends do, whatever. Okay, so the Hebrew alphabet is actually the notation for that. This is a new letter, so like you don't see this. Okay, so that letter is called Aleph. Okay, so this is from the Hebrew alphabet. Okay. And we assign this to be Aleph 0. Okay, so we call this Aleph 0 as the cardinality of the set of natural numbers. Okay, the cardinality will not be equal to plus infinity, guys, as you see. Okay, you will actually know this. So this is a cardinal number as well. Okay, so this is the cardinality, or this is a cardinal number. All right, and that would be equal to that of the set of natural numbers. So this is the cardinality of the set of natural numbers. Okay. All right. This is kind of weird, I understand, right? But you don't have to be afraid of this. Okay, so don't be afraid. This is just an abstract definition, so we have to call it somehow, let's say. Okay. And the Greek letters are gone. All right. So we take the Hebrew letters as well, okay, and after that probably we take the Chinese alphabet, I'm not sure, okay, but we have to call it something. I mean, this is how it is, right? So these are the sort of cardinal numbers, so cardinal numbers, and we, as you can see, we extend, we extend the set of natural numbers because all natural numbers can be, of course, cardinal numbers, but not all cardinal numbers are natural, as you can see. So for instance, the cardinality of the set of the numbers, okay? Now, guys, okay, so let me just continue with the next definition. Okay, so let's say, for instance, if the cardinality, okay, and I'm going to write it like this. So if the cardinality of a certain set is strictly less than that of the natural numbers, okay, so Aleph 0 is the cardinality of the natural numbers, and if a set has a cardinality which is strictly less than that, then the set A is called finite. Okay? So the set is called finite. You know what I'm saying? Okay. All right? So that's the first definition. It's called finite. It is strictly less than the number Aleph 0, which is a new number. This is a new concept that you might not be familiar with. Okay? Again, so this is the Hebrew alphabet. All right? I mean, that's actually where the name alphabet comes from. So Aleph, Bet, these are the first two letters of the Hebrew alphabet, right? Okay? So if, let's say, for instance, on the other hand, if a set has a cardinality which is called, and then, okay, so here the cardinality is Aleph 0, then A is called countable. All right. Okay, so here in that case, if a set has a cardinality which is then exactly equal to that of the natural numbers, then the set is called countable. All right. And if, let's say, a set has a cardinality which is greater than that of the natural numbers, then A is called countably infinite. Okay. Or not countable. Okay. All right. So I used to say, I mean, countably infinite or not countable. So this is, I mean, no, let's say, sorry, I mixed it up, guys. No. These are the uncountable sets. Okay, so these are the uncountable sets. Okay. Okay, I apologize. And again, I'm not in the mood as I used to be. Okay, I hope it goes away. Stupidity sometimes remains. I hope it's not going to be the case here for instance. So, no, sorry guys. This is called countably infinite. Okay, I mixed it up. I apologize. Countably infinite. If the cardinality is greater than that of the natural numbers, then it's uncountable. And countability means that it is either finite or countably infinite. Okay? So finite or countably infinite. I apologize. Okay, so let me again, because that was kind of bad. Okay, so if the cardinality of a set is strictly less than that of the natural numbers, then the set is called finite. If the cardinality is equal to that of natural numbers, then it's called countably infinite. And if it's either finite or countably infinite, then it's called countable. So I use the expression countable set for sets that are either finite or uncountably infinite. And if the cardinality of a set is strictly greater than that of the natural numbers, then the set is not finite. Yes?
Is there any example?
Yes.
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 For countably infinite set that is not L of itself?
Yes. I mean, no, there is no, so that it has to be equal to that of the natural numbers. But I'm giving you an example. What you mean is that is, for instance, an example to a set which is not equal to the set of natural numbers, but is countable. Okay. Yes. And I'm going to give you the example, the set of all integers. Okay. So here, of course, let me just define this. Okay. So the set of natural numbers, including 0, is, as you've seen, 0, 1, 2, 3, etc., etc. And the set of integers denoted by capital Z. Remember that. Okay. So the set of integers is 0, 1, -1, 2, -2, etc., etc. Right? Okay? Now, guys, this is kind of interesting because you see that the set of natural numbers is a strict subset of that, of the integers, right? So this is the set of integers, and this is the set of natural numbers. Okay? Now, we can show that, and we will see this. Okay? So we can show, all right, and this is kind of weird, that the set of natural numbers has the same cardinality as the set of integers. Okay. Is it now? Is it working? Yes. Okay. What happened there? Is this some kind of mystery or something?
No, the thing wasn't stable.
Okay. It wasn't safe anyway. Okay. So basically, you can see that the set of integers is countable. Okay, so both sets are countable. Although, all right, so although actually the set of natural numbers is a strict subset of the set of integers, right? So you have to understand, and this is actually the proposition here, and I'm going to prove that. So here I'm going to demonstrate that this is not actually difficult to do. All right, so this means that there are just as many natural numbers, guys, as integers. Okay, so that there are no more integers here in that concept than natural numbers. And why is that? Because, and what does that mean? Because there is a bijectivity between the set of natural numbers and the set of integers. Okay, so there is at least one. Now let me define this bijectivity. So let me define the bijective function here. Okay, so we define this as follows. Okay, so for instance, we define f as follows. Okay, so after we, as you can see, so the arguments of the function will be the set from natural numbers, and actually the images will be the set from real numbers. So the argument, let me just, okay, so use these markings because you understand it better. So these are the set of natural numbers. So you have 0, 1, 2, 3, etc. And here you have the set of integers. Okay. All right. And I'm using these notations so you understand it, you see this better. So for instance, what would be the image of 0, guys? So the image of 0 would be 0, right? Same thing. Then the image of the number 1 would be 1. Okay, so this is how we move. All right. Then the image of, let's say, the number 2 is, or would be what? Would be actually -1. Okay? Sorry. So to see it better. What would be the image of 3? The image of 3 would be 2. Yes. You see? Etc., etc., etc. We move on. Okay? You understand this? Okay? Alright, so we define this function implicitly. Now guys, this function is bijective. Okay? Because two different arguments always going to have two different images. That's clear. Right? So if the arguments are different, the images are also different. And there is at least one pre-image for all elements of the set of, actually, from the set of all integers. You can find always actually a pre-image to which this element is assigned to. You understand? Okay? So this function is bijective. Okay? Then f is obviously bijective. And remember, the sets were called of equal size, right? If there exists at least one bijective function between the two sets, right? You understand this? I mean, that was actually the beginning of the first part, where we had the set A that has 3 elements, and the set B had also 3 elements. And you know, we could actually define a function on this set where one element from A is assigned to one element from B in such a way that two